For rapid advances in technology, the ability to work virtually in 3D is now common. Today we will be exploring two very distinct environments that utilize 3D technology. We'll start with industrial automation. Factories are generally very dense with equipment, people, and machinery. A traditional 2D layout will only depict a single layer, usually on the shop floor. Cable trays, conveyors, and piping systems will frequently go undetected in these plans, making clash detection difficult to impossible. These interferences will result in field change orders, project delays, and cost overruns. A true 3D as-built condition is required for efficient collaboration and project control. Because of the complexity of industrial automation, 3D technology has been utilized for over 15 years. The demands of shorter cycle times required planning, modeling, and simulation for verification before any work was done at the plant. It was imperative to have an accurate as-built model of the plant in order to utilize the new digital technologies. Probably the greatest impact of 3D factory technology has been reduction in construction times. All design and validation can be done digitally with assurance of accuracy before the plant is scheduled for shutdown maintenance. This also results in reduction or elimination of field change orders, greater project control, and collaboration. Going forward, the plant will have a complete asset database of all equipment installed on the shop floor. Instead of spending hours manually sketching out factory assets, you can now get them for free from ever-increasing libraries of parametric factory objects. Factory design software now includes a wide range of smart objects such as conveyors, material handling equipment, robots, electrical equipment, and facilities content, and it makes it easy to resize and edit assets based upon your layout requirements. You can now present your layouts in 3D so anyone can understand the design intent. 3D Factory enables you to create compelling 3D visual fly-throughs and walkthroughs of your machine layouts and share it with your clients and non-technical stakeholders. This not only enables you to clearly communicate your layout ideas in 3D, but also helps you to differentiate over someone who is communicating layout ideas in 2D. With this rapid comparison capability, you can identify any potential problems before equipment is installed or commissioned on the factory floor, and still create traditional 2D paper deliverables for your installation team, all from the same source data. The features of 3D Factory have bottom-line results. Multi-CAD support gives you the ability to work seamlessly with native CAD data from a wide range of design systems. Visual fly-through and walkthrough gives you the ability to handle the entire factory floor layout. You can aggregate data from design systems into a single environment to build a single digital factory model. Support for laser scanning workflows will capture the as-built state of the facility and the capability to design layouts in context of the laser scans. Also, clash detection capability between the laser scan point cloud and the 3D layout model. Additionally, clash detection will make sure the layout is free of collisions and not violating space constraints before the equipment is installed and commissioned on the factory floor. Collaboration tools will allow you to easily communicate the layout design with suppliers and partners. This chart shows the effect 3D workflows can have on the number of field orders seen on the typical factory construction projects. These numbers are from a series of real projects done with one of the world's largest manufacturers. They show the progression from typical 2D processes to advanced 3D implementations and field orders dropping from over 35% of total project cost to less than 5% with 3D workflows. In 2002, General Motors began using 3D models and laser scanning to quickly update the layouts for the existing general assembly and body shop facilities internationally, quickly adapting the process as a key use in future program modifications. PMC has converted and completed over 6 million square feet of plant floor to functioning 3D models. Using 3D digital engineering, cycle times can be reduced, field change orders eliminated, with overall cost reductions. In 2012, a large automotive manufacturer needed to install the fifth in a series of identical heat treat furnaces. For the 4 previous installations, the decision was made to remove the roof and raise the bottom chord of the truss by 10 feet. When production needs drove the decision to install the 5th furnace, plans began to raise the roof line once again. PMC was able to scan and work with a structural engineer to design a plan that eliminated the need to raise the roof line of the building. The largest obstacle to 3D Factory is the huge inventory of existing facilities remaining in 2D formats. 3D laser scanning can be used as a segue. This case study is a new well water line for an automotive plant. The plant layout was in 2D, and the architect designed the new line in 2D. The OEM wasn't convinced of the accuracy against potential clashes due to the density of the MEP in the planned route. PMC's solution was to 3D scan the route of the proposed new line through the plant, then convert the architect's drawing from 2D to 3D inventor model, and overlay the model into the scan. A series of collisions were detected, including existing piping, fencing, and numerous light fixtures. This study, which was completed in under 2 weeks, saved an estimated $60,000 in field change orders, and more importantly, valuable time lost in new fabrication. I'd like now to move on to our second application for 3D technology, Building Information Modeling, or BIM. In the 2D world, lines represent elements in a building. In BIM, there are no lines. Everything is an object in a 3D world. These objects are shared throughout a facility in one model. Change the object once, and it changes throughout the facility, eliminating duplicating changes and mistakes. We can then elevate the model to incorporate all associated records, documents, thus creating a single source of truth. BIM is first and foremost about early and ongoing collaboration, continuous improvement, and robust lifecycle management process supported with integrated technology and standardization information. This is a sample from a Revit model. By clicking on the small window, which is outlined in blue, the properties of that element are displayed in a pop-up window. These include dimensions, manufacturer, finishes, etc. This data can also include asset management information, such as projected replacement date or date last serviced. BIM adoption remains a challenge due to the fact that its many supporters don't focus on its true relevance, the efficient lifecycle management of the built environment. A smart building is the integration of building, technology, and energy systems. These systems may include building automation, life safety, telecommunications, user systems, and facility management systems. Smart buildings recognize and reflect the technological advances and convergence of building systems, the common elements of the systems, and additional functionality that integrated systems provide. Smart buildings provide actionable information about a building or space within a building to allow the building owner or occupant to manage the building. The real value of BIM is post-construction. Historically, facility management required numerous systems to collect and manage data. Floor plans, photos, plan elevations, building maintenance schedules, and building automation systems were routinely in separate sources, often in separate departments. With the introduction of BIM, owners and facility managers can optimize the way that buildings are designed, built, managed, and retrofitted. Flexible technology tools can bring together BIM models, data, and operational systems integrating with facility data management systems. This environment provides a single source of truth with support for open standards such as COBie. For organizations that will maintain legacy facilities in existing 2D, laser scanning can be used to collect a 3D representation of the facility, thus providing the ability to track assets in all locations. There are added advantages of having 3D data, such as using the point cloud for safety briefings for contractors and repairmen. The traditional X's and O's on a whiteboard can be replaced by a digital walkthrough. This video shows a point cloud, which is the complete record of the building, including geometry. The process of producing this data is to combine the individual scans during registration and create the point cloud. 2D drawings and elevations, or a 3D model, can be drawn from the laser scan point cloud. This is a sample of the Revit model created for this project. Product documentation, such as submittals, data sheets, warranty, and specifications, are attached to assets, systems, locations, and facilities. The BIM model will associate location and provide visualization. Visualizations of assets in 3D can be used to track mechanical, electrical, plumbing systems, and identify areas of concern, such as a plumbing leak. 3D visualization improves the overall coordination of systems, saving time and money. Building automation systems, such as energy optimization, security, and fire protection, can be integrated with BIM, providing the system's data in a 3D visualization format. Once the 3D model is completed by the architect, element data can be incorporated. A virtual mock-up of materials, or takeoff sheets, can be created, giving an accurate costing of the project. Additionally, accurately placing the model in the civil site plans before construction in a digital model can identify incorrect or missing parts of the model. COBie, or Construction Operations Building Information Exchange, was developed by a number of U.S. public agencies to improve the handover process to building owners and operators. The primary goal is to ensure that owners receive the information about the facility in as complete and as useful a form as possible. COBie is a non-proprietary format based upon multiple-page spreadsheets which can be integrated with 3D models for visualization and collaboration. The real value of BIM is post-construction. If the maintenance staff needs to access manufacturer's data on equipment, how many steps does it take? 5, 10, or more? There can be great savings on staff time of not having to take a half day looking for documents. A basic task, such as changing a light bulb, can be simplified if the maintenance staff knows exactly the bulb type and manufacturer that needs to be replaced. All of the building elements can be identified with their associated documentation, such as warranty and maintenance log, in a single source. This will allow for more accuracy in maintenance planning, asset management, and provide the data for general capital improvement budgets. While big data is a phrase most commonly associated with the financial and retail sectors, it has finally come home to roost in AEC, especially with the large amounts of highly trustworthy information using BIM technology and related systems. Using big data analytics to drive down the number of mistakes made in the real world, in everything from asset design to operations and maintenance, is key. It's far cheaper to get it wrong virtually than in reality. The phrase "if only" should disappear from the lexicon of project planning, design, and delivery. The productivity boost alone will be a boon. PMC has over 35 years of experience as a leader and innovator in digital engineering solutions for facility design and optimization throughout the life cycle of a project. From concept to commissioning, let our team of experts show you the answers to your challenges.